Okay, welcome back. We're going to take our first look at how to find the lengths and angles in non-right angled triangles. This, of course, means we're not going to have a 90-degree angle, the one that we depend upon for us to be allowed to use sine, cosine, and tangent. Now, we are going to be using the sine ratio and the cosine ratio, but in an entirely different way. So let's see what we have here. Here's such an example of a triangle. Oh, and before I get started, I want to remind you that the angles in any triangle, whether it's right angled or otherwise, add to 180 degrees. So here we can see that here's a triangle with a 45-degree angle and a 30-degree angle. Of course, 30 and 45 add to 75, which means this remaining angle over here must be 105. It's not labeled, it just has to be true. And they've given us one other side. Now, the essence of trigonometry says that if you have any three pieces of information apart from three angles of a triangle, you are in a solvable situation for any other side or angle in the triangle. So that means theoretically, using the powers of trig, we could solve for anything in that triangle that you see there. Okay, so let's move on here. Before I get going, again, we need to cover some of the basic ground rules. If you're going to be labeling a triangle, we use capital letters to indicate the vertices or the corners of it, and we use lowercase letters to indicate the sides, and they always match up one across from the other. So you can see that across from side B is angle B, the angle at vertex B, and that's the same all the way across the triangle. There's the lowercase letters, and they sit directly across from the angles. Sometimes we'll label the angle inside, not just the vertex, and we use a lot of Greek letters here. You can see the letters alpha, beta, and theta were chosen, but all the Greek letters are accessible and usable. Here it is, the sine rule. It comes in two different formats. It's in your formula kit, and in this particular case, it says that the sine of any angle divided by its opposing side. So the side, say, of the angle at A divided by the side length across from remains constant throughout any triangle. What does that mean? It means it will be true whether it's the sine of angle B across from its side, opposing side, or whether it's angle C across from its opposing side. And of course, all three of those fractions could alternatively be written in their inverted form, where the side lengths take the superior positions and the angles take the inferior or the bottom positions of those fractions. Right. Now that's an unusual looking formula. You don't usually see formulas with two equal signs, but let me sort of demystify what's going on here. Before I do, I'm just going to show you some examples of when you might use these kind of things. If I'm looking for this side length here, I might refer to this as side A because I've got an angle over here at A, and we could say that this part of the sort of three-phase formula is what we want. This part is of no use to us, so I can just ignore it, and I just sort of chop up the parts that I do want. I might also use this one here because this is the unknown, and since side A is there, I would call this angle A. And again, this part in this particular case is irrelevant, although it could be relevant in another question. There is a triangle QRS, whose length from Q to R is 15, whose length from S to R is 6.5, and whose angle at S is 125 degrees. Well, already you know it can't be a right angle triangle because 125 is a large obtuse angle. There's only 180 degrees in any triangle, and once you remove 125, the other two only have, 55 to share. So that can't be a right angle triangle. So what I'm going to do here, what's going on here? This is a case where the triangle is not actually shown, it's referred to in terms of words. So here's what we're going to do. I'm going to draw a flat line. I'm not concerned about its length. I just want to get a flat line that I can start working on. And from here, I'm going to draw with my protractor. Again, we're not trying to draw to scale, but we want them to be close enough that we're not going to deceive or confuse ourselves later on. I'm going to draw a line that's approximately at a 125-degree angle. So I can see already that I'm dealing with this issue first. The first thing I try and do is get at least one accurate or pretty accurate angle. And that angle is going to be right in here, and that's going to have to become letter S because it was the angle at S. That was 125. Next, put that aside for now. And what am I going to draw now? I label that with an S and a 125. It said that from S to R was 6.5, so I can just choose. I chose to put R over here, and I labeled it with 6.5, and it's pretty good. The other missing vertex in the triangle is Q, and it's got to be 15 away from R. Now that's a little bit tricky. If it's going to be 15 away from R, that's going to put it over here somewhere. And remember, it's 15 from R, not from S. So I'm going to label that with a 15. And that's it. I've got a triangle. I've got a triangle with 3 known numerical bits of information, so that's enough to solve for anything else I want, so long as I have the right tools. And the sine law is one of these really good tools. What shall I do now? I'm going to take a look here, and I can see that sine law is the one to use because this is what you're kind of looking for. It's called a side angle partnership. If you ever know a length of any one of the 3 sides of the triangles and the angle that sits across from it, that's a dead giveaway that you're going to be using the sine rule. Let's see how we're going to do that now. They said find the angle at Q. Notice that these 2 bits of information here are the side angle partnership, and 6.5 is over here, and it sits across from angle Q. That means I can use the sine rule because it says any angles, the sine of any angle divided by its opposing side is always fixed. And this side angle partnership here is going to occupy an entire part of a fraction for us. This is what I mean. Take a look at this. So I've got the sine of angle S over its opposing side, 15, that's what I got here, is going to be the sine of angle Q across from its opposing side, 6.5. Now you can go ahead and cross multiply if you feel like you're some sort of hero. I just go ahead and get my calculator out, and starting from that stage right here, I don't bother with any of this stuff. I mean, you can just go to NSolve. You can see you get the same answer either way. NSolve is just so clean. I would recommend it. And so we would say, of course, according to the rules, 3 significant figures, that's 20.8. Remember, significant figures is the first 3 numbers, and then the 4th one decides on the fate of that preceding digit 7, and since 9 is quite large, it pushes it up to be 0.8. Another question, this is one of these worded problems. It says a ship is on a bearing of 120 degrees from port A. Well, this is the bearing work we were working on recently, right? And 42 degrees from port B. Whoa, this is pretty tricky. Okay, let's see. The distance between the ports of A and B is 15.2 miles. Find the distance between the ship and each of the ports. Okay, what does this mean exactly? Let's take a look here. There's our compass, our protractor, beg your pardon. Remember, you don't hold a protractor flat like it's half of a sunset or half of a sunrise. You hold it vertically like that because we're going to be using it to measure from north, and north is vertically up the page. It says there is a ship on a bearing of 120, so I'm just going to point a line out at a direction of 120, and I'll let the ship go there somewhere. He's sailing away, off he is. And then it says if you go over to port B, that ship is also at a bearing of 42 from there. I need to do it backwards. And I go over to here and I draw a 42. And now you can see that the ship has to be on both of those pathways. So that means the ship actually has to be there because it is on a bearing of 120 from here. Now you'll notice I've drawn the 60 in here because the 60 is in the triangle. The 120 was drawn to show us its relationship to north because that's how bearing works, but I had to push it forward to find out that 60. And I've got a 42 down here. Those add up to 102. That means that we don't have a right angle triangle. They also said that the 2 ports are known to be 15.2 miles apart from one another, so I can take advantage of that, and that's it. I've got 3 pieces of information. Now, it might look like sine rule is not an appropriate tool to use here because I don't have what they call a side angle partnership, or an angle that's known and the side across from it known as well. Unknown. Over here, unknown. It does look like we might be out, but remember, the angles in a triangle have to add up to 180, so indirectly, you kind of are only a step away from knowing the 3rd missing angle here. And I can go ahead and write that down. That one's not known. That one's not known, but I can work out the missing angle at S if I know the 60 and the 42. So I'll just write down that at 78 degrees. And that's 180 minus 60 minus 42. Right, so I got my sine law there again. All I need is to take advantage of any angle, the sine of any angle, and the side across from it set equal to any other sine of angle divided by the side across from it. So I've got this. They said to find the distance from the ship to each of the ports, so I've got a big job to do. I've allowed this one here to be 15.2, the known distance between the two ports, and the angle between them is going to be, the angle at the ship here is going to be 78. From that, I'm going to have two separate problems here. I'm going to have to do the sine rule once to find A and then once to find B. I've elected to go with B first, no particular reason. I'll move that aside, and I just temporarily ignore this. It's not in play right now. And that's the main part. Now you could go ahead, be a hero, and do that with the cross multiplying and everything else, or you could just end solve it and you get the answer of 10.4. If you wanted to solve it using cross multiplication, you'd get the same answer. You'd just take a few more steps and expose yourself to slightly higher risk. If I want to go after A now, I can do that. I just set those two equal to each other in a new equation. There it is. And again, I'm not here for the medals. I'm here for the correct answers. So I'm going to go ahead and do my end solve and find out that the answer for A is 13.5 approximately. Now, I was saying to you earlier in this course that trigonometry is very handy for finding inaccessible lengths, and that's exactly what we're going to do here. So we got a sailboat out there, and you can see that the sailboat makes an angle with one observer and the shoreline at 65, one at 42, and we know that those two observers are 20 meters apart. That's it. You can figure out anything you want to know. Find the distance from sea to the shoreline. Now, that's kind of weird because the distance from sea to the shoreline is actually a straight line that comes in perpendicularly to A and B. So I'm looking at a line that kind of looks like here. So it's not part of the original triangle. That doesn't matter. What I do need to do, however, is find something out about the triangle that does include this red line, and that's namely this length or this length, and I can work back to find out this missing length here using regular right angle trigonometry. What do I mean by all that? Well, I'm going to put the 73 back in there. That's the difference between these two numbers and 180. So I found that to be 73. I know an angle and the side length across from it. So that basically is the gateway, the ticket to using the sine rule. And I'm going to just pick one of the sides at random. That green one there I've labeled over here. I'm going to go ahead and find that. That's going to be side length A because angle A is over here, and that's the naming convention that we use. So I'm going to go ahead and set that equal to 20 over the sine of 73. And drop it in, solve on that, and I can see that it's 18.9544. Now, I've set my calculator round off this way, but behind the scenes, the calculator is actually remembering a lot more. So if I now wanted to go ahead and find x, I could do that by noticing that the sine of 42 degrees is x over 20. Not x over 20, sorry, x over my preceding answer, which is what I've done here. I've written preceding answer down. Now notice what happens when I hit enter on this. It changes it to be the actual number. Now, even though mine was rounded off substantially to 18.9544, the calculator remembered it with much more precision. And that's how we get the answer of 12.683. And that's how far the boat is away from the shoreline. Why is it doing that? There it is, 12.7. Okay. We're into 2A. Some nice questions here. There's only 3 questions. I mean, the first one's got 3 parts, so I guess it's like 5 questions in total. Can you get started, please? I'm here to help you. And there's your list right there. Okay, good luck.